Okay, so we're going to look at some example problems involving infinite limits. Here we got 4 different graphs, and they're all based off of the rational graph of 1 over x minus 1. So you see we have, 1 over x minus 1, we've got negative 1 over x minus 1, we've got 1 over x minus 1 squared, negative 1 over x minus 1 squared. So we're really mainly looking at this point x equals 1 from the left and the right side. And based on the behavior of the graph, we're going to say whether or not it has a left-sided limit of negative infinity or infinity. So for our first graph, our limit as x approaches 1 from the left of f of x, well, we look, our graph is going straight down after a while, so it has unbounded behavior and it is approaching negative infinity. For the limit as x approaches 1 from the right side, well, from the right side of 1, so over here, looks like our number's going up, right? So this is going to infinity. Now, if we keep moving along, right, our limit as x approaches 1 from the left side of this f of x, well, this one is going straight up. Well, that's because the denominator is being squared, right? It has to be positive. So as we get closer and closer to 1, our denominator is getting closer and closer to 0 from the positive side. So this ends up being a regular infinity. And when we look at the limit as x approaches 1 from the positive side, we can see it's still doing the same thing as it was earlier, which is going to be approaching infinity. Then we have our limit as x approaches 1 from the left side of f of x. In our third example, this one is working kind of as a complete opposite, or as a reflection of our original graph. Anytime you just make a graph negative, like we've done between these two, you're going to flip them. So instead of f of x going to negative infinity from the left, it is now going to infinity. And we can see that is occurring here. And then we have our limit as x approaches 1 from the right side of f of x. That is approaching negative infinity. And again, we can see that it's going down. And then lastly, kind of in contrast to the example B, we are going to have both of our limits approaching negative infinity. They're both going down. And that's because two things. Our numerator is always negative, and our denominator must always be positive. So we're always going to have a negative number, no matter what, except for when we have our asymptote here, of course. And then finally, you said our limit as x approaches 1 from the right side of f of x, that's going to be infinity. So how do I go about finding vertical asymptotes? Well, vertical asymptotes are going to exist when our denominator is 0. So denominator is 0, and we have some number at top. So that's going to be when we have a vertical asymptote. Okay, so what we need to mainly look for is when our denominator is going to be 0, and test to make sure that that doesn't cause 0 in the numerator as well. So for A, we want to see when 2 times x plus 1 equals 0. So we get 2x plus 2 equals 0, 2x equals negative 2, and x is going to be negative 1. So that cannot make our numerator, which is 1, 0. So this is our first answer. B, we want to know when x squared minus 1, when that equals 0. Well, we get x squared to equal 1, and x is going to equal positive or negative 1. Now, if we were to plug those numbers into our numerator, we would always get a number, which means that we have a vertical asymptote. Be very careful that when you square negative 1 squared, that equals negative 1, but negative 1 squared, which is what you'd be doing, that equals 1. Very, very different answers, okay? So be careful. So these are both going to work. And lastly, for C, we've got f of x equals the cotangent of x. Well, the cotangent of x, in case you remember, is the cosine of x divided by the sine of x. So we need to know when our sine of x equals 0, because it's the denominator here. Well, the sine of x is going to equal 0, so x will equal, this will work whenever we have a multiple of pi. And you say, where k is an element of your integers. Okay, so anywhere where we're at pi or 0 or 2 pi or 3 pi or 4 pi or 5 pi or negative 1 pi or 2 pi, so on and so forth. These are where we're going to have our vertical asymptotes of this graph. So let's look. So determine all asymptotes for this graph. Okay, so this is one where we're going to want to make sure that we are plugging everything in the right way and double checking. Okay, so we've got, first things first, we want to know, again, that if we have a number over 0, that equals a vertical asymptote for us. Okay, so we're going to look at x squared minus 4 equals 0. So we get x squared equals 4, and x is going to be positive or negative 2. So we want to test to make sure that these numbers work, because we are definitely in danger of either of them being bad numbers for us. So we go ahead, we plug in our first number, which is, we're going to try negative 2. So for negative 2, we get negative 2 squared plus 2 times negative 2 minus 8. So we get 4 minus 4 minus 8. So that gives me negative 8. So we're good. So this is a vertical asymptote. Now if we plug in the number 2, we'll get 2 squared plus 2 times 2 minus 8. So this is 4 plus 4 minus 8. That does equal 0. So this is the indeterminate form. Which means that 2 is actually a factor of the numerator and denominator. So this is not a vertical asymptote. It's not going to be it. So the only one that we are going to necessarily have is, so x equals negative 2. Okay, so now we're going to look and finding limits using infinity. Okay, first one we have here, so we've got the limit as x approaches 1 from the left of x squared minus 3x over x minus 1. So what we want to see is, are we getting the indeterminate form or are we not? Well, if we plug in 1, okay, so we need to see, do we have a vertical asymptote or not? Again, a number over 0 is a vertical asymptote. A 0 over a 0 means, a removable discontinuity. Okay, so that would be the difference between these being, this would be something like, and this would be, okay, so different, big difference there. Now, in this case, we're going to if we plug 1 in, we're going to get 1 squared minus 3 times 1 over 1 minus 1, which gives me negative 2 over 0. So we know that that's a vertical asymptote there. So we need to figure out, does it approach 0 or does it approach, does it approach infinity or negative infinity? Now we don't want to just look at this. We want to make sure that we're really paying attention to what we're doing. Okay, so in this case, our numerator doesn't matter. Our numerator is always going to give us this negative 2 value. Our denominator is what we're really concerned with. What kind of 0 is this? Is it a positive 0 or is it a negative 0? Well, we just need to look back and kind of make that determination for ourselves. So this 0 here is going to end up being negative. And why do I know that? Well, if I have a number that is less than 1, and I subtract 1 from it, do I have a positive or negative number? I'm going to have a negative number. Okay? So I'm going to end up with negative 2 over negative 1 over infinity, which based on our math, we get negative 2 times negative infinity over 1, which gives me a positive infinity. Right? So very important to go back and make sure we're checking, because this negative on top ends up getting undone because our number ends up being smaller than infinity, or smaller than 0. Our second one, the limit as x approaches 1 from the positive side, you can probably guess as to the fact that it's going to be a negative infinity here. Okay, so we go through. We plugged 1 in. 1 squared minus 3 times 1 over 1 minus 1. That gives us negative 2 over 0. What we need to figure out is my denominator, is that a positive 0-ish or is it a negative 0-ish? Well, if I have a number greater than 1 and I subtract 1 from it, I should still have a positive number. So I'm going to end up with negative 2 over 1 over infinity. That's what we're calling those. So you end up with negative 2 times infinity over 1, which is just going to be negative infinity. Lastly, we're just going to look at some simple properties here. If I know the limit of 1 as x approaches 0 is 1, and so the limit of 1 over x squared as x approaches 0 is infinity. So if I were to say something like, what's the limit as x approaches 0 of 1 plus 1 over x squared? Well, logically you would be like, oh, well, I just add 1 to infinity, which is true. And then this just equals infinity. Okay, so we're just trying to scale it, just trying to show that what happens when we deal with infinity algebraically. Then we have, okay, so the limit as x approaches 1 from the left of x squared plus 1 equals 2, and the limit as x approaches 1 from the left of the cotangent of pi times x equals negative infinity. So how would we want to write this? So we'd say, okay, well, what about the limit as x approaches 1 from the left? And let's say we had a function that looked like this. X squared plus 1 over the cotangent of pi x. Well, I can look at these two separately, right? If I know that the limit of the numerator is 2, I can replace it with a 2. And if I know that the limit of the denominator is negative infinity, I can replace it with negative infinity. Well, what is this answer going to look like? If I divide 2 by negative infinity, this 2 just ends up becoming so insignificant that this is going to pretty much become 0. Now, even though you've got this negative down here, any number divided by an extremely large negative number is going to be very, very, very close to 0, just like it would be if it was positive. So over time, though, the limit, it's trending to be towards 0. And then lastly, if we have, let's say the limit as x approaches 0 from the positive side of 3 cotangent of x, we know that the limit of 3 is 3. We know that the limit of the cotangent is infinity. So this just ends up being like the limit of 3 times infinity, which again is infinity.